Okay, so this is lecture 2, where we're going to talk about diffusivity, permeability, and diffusion through membranes. We'll skip through that. Okay, this is an example of the type of problem that we'll be dealing with today, where a drug might be enclosed in a membrane, and the membrane permeability will affect the release of the drug. And so things we might want to look at is, what is the permeability of the membrane, and what is the rate of drug delivery from the membrane? So these are the things we're going to address in this lecture.
Oops. Right, you get to see the blooper reel. Also, hi students.
Do we need to plug that in?
And it'll last. We should finish before it runs out of battery.
Okay. So we're going to start off by reviewing Fick's first law. We looked at this last time. Basically, the flux is just... can I change the color of this?
Yep. Let's make
it red today.
Okay, you have red.
So the flux, and a little bit bigger.
Mm-hmm. Actually, maybe restart.
Yeah, let's restart.
Mm-hmm.
Yeah, that's good.
Okay.
Going to start at the beginning? Yeah.
Take 2.
All right, here we go. Okay, this is lecture 2, where we're going to talk about diffusivity, permeability, and diffusion through membranes. And this is an example of the kind of problem we'll be addressing today. You might have a drug that's enclosed in a membrane, and the membrane has a permeability to that drug, and it will affect the release, the rate of release of the drug. So example things we'll look at is, what is the permeability of the membrane, and what is the rate that the drug is being delivered through the membrane? So we'll look at things today that can answer that. And I'll just skip over that. We talked last time about Fick's first law of diffusion, and we saw that the rate of diffusion, the mass, let's see, that's the molar flux, is proportional to the concentration gradient. There's a negative sign, and this is the diffusivity. In 3 dimensions, it is this, but usually we'll just be looking at 1 dimension. Now, let's talk a little bit about the diffusivity. If we take Fick's first law and solve for the diffusivity, and then just look at the units, we find that the units for diffusivity are length squared over time. Usually it's things like centimeter squared per second, meter squared per second. These are some examples of the ranges that we see for diffusivity. In gases, it's like around 10 to the minus 5th meter squared per second. For liquids, it's around 10 to the minus 10th, which is 5 orders of magnitude less. And for solids, it can be even less, like 10 to the minus 14th or so. We can, for a liquid where there's a non-electrolyte in it, in a dilute solution, we can estimate what is the diffusivity for that non-electrolyte in liquid B.
Why is it different for electrolytes?
I guess because of the charge.
Huh. That would make sense, yeah.
and that is my guess. So anyway, we're going to use this. It's just a correlation, an empirical correlation of experimental data. And so here we see the diffusivity. We can estimate it if we know the temperature, if we know the viscosity of our solvent B.
Okay.
And viscosity is just a measure of how thick or the resistance to flow for the fluid. Let's see, this is an association parameter that you can find from your book. This is the molecular weight of the solvent, and this is the molar volume of the solute at normal boiling point.
And so all of these things you just look up in a table somewhere.
Exactly. And,
Okay. That makes this equation look much less scary.
and one thing you have to do is make sure that you're using everything in these prescribed units.
Okay, yeah, so unit conversions need to happen here.
Right. No. Right. Just use the units as they're listed here, and then you will get the diffusivity. Let's see, in units of centimeters squared per second.
Okay.
One thing to note from this empirical relationship, if you multiply by t, so you bring the t over to the right side of the equation, you can see that the diffusivity is more or less proportional to the temperature, which means that as the temperature increases, diffusivity increases, which makes sense.
Right, because you've got more of the Brownian motion, things are moving around.
Exactly. And also this viscosity term, if you divide by viscosity term, so that's 1 over viscosity on the right-hand side, if you increase the temperature, the viscosity of the solvent will go down. It will become thinner. And that means that, one more time, that's just one more reason why the diffusivity will increase if you increase the temperature, because the viscosity will decrease.
So far, this makes sense. So this is basically just, here is a mathematical language for describing the physical world that we've all sort of intuitively experienced.
Right. And there's no justification for this equation other than it fits the experimental data. This was not derived. It's just an empirical fit. Okay. This is an example where she is calculating the molar volume of ethanol in order to put it into this equation if ethanol is your solute that's diffusing. This is, let's see, in this table, you see some molar volumes here for certain substances. If we're looking for ethanol, ethanol is not in this list, so we're going to go to this table and we're going to look at the different components. Like ethanol has 2 carbons and I forget how many hydrogens, 6, and there's an oxygen here. Okay, so you would add up those components as she did in the previous slide.
Okay, so it's like Lego your molecule together.
Right.
We'll use one from our pre-assembled list, conveniently made for you.
Exactly. And now this is our phi, our attraction. Here. Right.
The association.
The association parameter. So that comes from, whoops. She doesn't list the table, but it's in the previous slide. So you can find that in the book.
Okay, so a lot of it is just like, go find a number, plug it in. Exactly. Now it's algebra.
Okay, and now, if you take, I have to go back. Where is it? Here. I'm sorry for going all over the place. The diffusivity, remember, is L squared over T. Oh, we've got your chair. Do you need your chair back? Okay. Diffusivity has dimensions of length squared over time. And so if you move that around, that means that time, some characteristic time, is in some length squared over the diffusivity.
Okay, just by moving units about.
Mm-hmm. Okay, so what that means is that the time for diffusion is large as the distance gets large because it's L squared. And so diffusion is diffusion is important at small distances and less important at the larger distances.
And that makes intuitive physical sense. Like if I have just a very small volume of fluid and I'm trying to get something to move through, I can just sort of drop that stuff in there. But if I want to get it several meters away, I probably have to do some mixing.
That's right. That's right. Let's see. In a lot of the length scales that we're looking at, diffusion is actually a very important process. Now, she's showing the difference between what's outside the fluid, a cell, and what's inside the cell. And, for example, oxygen, you can see it's 35 millimeters of mercury for the partial pressure outside and 20 inside. And so what that means is that there is a driving force for diffusion for oxygen from outside to inside the cell. Of course, where it reacts and is used up. Carbon dioxide is the other way around. It's there it is. 46 millimeters of mercury outside and 50 inside. So there's a concentration gradient driving carbon dioxide out of the cell.
And so this is how cellular respiration happens. So you've got oxygen that's pushing in.
Well, diffusion is an important part of that, of getting the oxygen into the cell and carbon dioxide out.
Cool.
For some substances like sodium,
oh, that's huge. That's a huge difference.
There's a lot of sodium inside and very little sodium outside, which means that diffusion would go into the cell. So there's some active transport of the sodium out of the cell at all times to counter this diffusion. And if you look at potassium, it's the other way around.
Okay, so and we're talking about this because I see the slide header talks about membrane permeability. So like, what happens? What keeps all this from just, all the sodium balances out, and then boom, we've got a very salty cell.
Well, actually, what's going on is there's a lot of active transport of sodium out of the cell and potassium into the cell. But the amount of active transport that you need depends upon how fast the sodium can diffuse into the cell. Okay. And so that is determined by the permeability of the membrane.
Cool. So we're just talking about the diffusion across the membrane. We're not talking here about the pumps getting the sodium back out.
No.
That's a different class.
We're not talking about the active transport. It's just an interesting sidelight of here. But we're going to discuss the permeability of that membrane, which is what determines how fast it can diffuse in and out. Okay,
right.
And this is where passive diffusion determines the permeability.
Like, hi, I'm sodium. I'm just going to mosey my way through this membrane.
Right, by Brownian motion. And facilitated diffusion is where it's still diffusion going from a high concentration to a low concentration, but it needs to be facilitated by something. Perhaps it's not soluble within the membrane, and so something is going to escort it through.
So like fat-soluble, water-soluble things dissolving
right.
in that, and then the water passing through the membrane.
Yeah, something like that. But it's still diffusion from a high concentration to a low concentration. Active transport goes against the concentration gradient, and so that takes energy.
And that is not this class.
That is not this class.
This might be a tangential thing, so stop me if so, but the facilitated diffusion with the carrier, so let's say you've got a water-soluble thing that's passing through a membrane. Would you be treating the carrier and the, vitamin C is water-soluble, I think. Yeah. So, like the vitamin C and the water, would you be treating them with the same species in your equations? Or would you have, concentration of water,
So, yeah, as it diffuses through the membrane, it would be the conjugate.
Okay.
the two, yeah.
So it would be like vitamin C in water, the species.
Yeah.
Cool.
Okay. All right, so what is permeability? It is defined by, well, let's just start with this equation. This is the, actually it's the rate in moles per second that the solute is being transported through the membrane. It depends upon the difference between the inside and the outside.
That makes sense.
S is the surface area, making this a rate, not a flux. And then we're going to take all of the diffusivity and other terms and just plop it all together in something called the permeability.
So P is like a permeability constant?
Yes, and it's really just, this is the diffusivity of the membrane, this is the thickness of the membrane. Here, folks. This is the thickness of the membrane. And let's see, this K is the partition coefficient.
I know we had some questions on the CIQ about partition coefficient. What is that?
So it is for a particular species and a particular membrane. It is the concentration in the membrane divided by the concentration in the fluid.
And is this another thing that you would go look up at a table?
Yes.
Okay, cool.
Yes. Okay, so like if this is a membrane, this is our membrane here.
Okay.
And this is our fluid. And so we have the concentration in the membrane. I can't write, it's not writing. So anyway, you have the concentration in the membrane and the concentration in the fluid. And the partition coefficient is how it's partitioned between the two of them.
So you just find a table of partition coefficients and you look up, I have this membrane, I have this fluid, what is this number?
Yeah, if you can't estimate it.
And is the G up here, is that a typo?
No, that stands for gram moles.
Gram moles, okay.
Yes, as opposed to, so that's the moles that you're used to dealing with in your chemistry class. It's just moles.
Just moles.
As opposed to a kilogram mole, which would be 1,000 moles.
Okay, cool. It's been a long time since I took chemistry, so this is kind of coming back for me.
Okay, and I won't scare you with other types of moles. We'll stop with there. All right.
I mean, my job in these recordings is to ask all the stupid questions, so.
Okay, so this is just an example of what the effect of pores can have on the permeability. And what's important is the ratio of the diameter of your substance, your solute. Like, for example, water has a diameter of 3 angstroms, and its ratio to the pore diameter of this particular membrane it's basically around 1/3. So it's kind of small relative to the pore, and it has a very large diffusion rate. As opposed to, let's see, a hydrated potassium ion is a little larger. Its ratio is around 1/2, not 1/3, and so its diffusion rate is decreased.
Oh, that's a dramatic drop there.
Yeah, it may have something to do with the charge as well, but anyway, there's definitely something to do with the size. And if you can imagine this molecule trying to pass through the pore, the smaller the molecule is relative to the pore, then the faster it will be able to diffuse.
Right, it's like, how big are the things that you're trying to get through this hole?
Right, so here's an example, and it also depends upon the geometry of the pore, whether it's kind of bent like this, or more straight, or wider or narrower. It depends upon the shape of the pore.
Okay, and that makes sense. And so we've got down at the bottom here we have F as shape factor and tau as tortuosity. And are those both basically fancy terms for how weirdly twisty is this pore?
Right. And now I can't speak for Dr. Babincy, but I do know that she did not stress a lot on that, so I don't believe it's going to be terribly important. Just something for you to know that if A is diffusing through B, and B is filling up this pore, then the more tortuous the pore, or the smaller diameter, then the harder it's going to be to diffuse. And so the diffusivity of the membrane, D sub M, is going to be less than the diffusivity of A through that solute B without any membrane in the way.
I mean, this all makes a lot of sense, right? If you put something in the way of diffusion slows down. Right. If you have bigger things trying to fuse through smaller holes, diffusion goes down.
Right. Okay, this is the partition coefficient here, and how the permeability is dependent upon that. This is a log-log plot, and it's pretty much a straight line.
And the partition coefficient was the thing we went to look up in the table based on it's this substance and this membrane and how fast do the two interact with each other.
Right. From this, the slope is around 1. That means, since it's log-log, that the permeability is proportional to the partition coefficient to the power of 1, which is, basically what we saw with our previous equation. Just kind of proving it. Here's the permeability again, relative to the molecular weight of the solvent, of the solute. Okay, right, so the permeability, in this case, once again, it's a log-log plot, but it's a negative slope, which means that, and I think that's around a slope of -1, so that's around -1, which means that the permeability is proportional to 1 over the molecular weight of the solute.
So as the molecular weight goes up, the permeability goes down.
Right, it's harder for it to get through.
And this one and the previous slide are just, here are how we found these values and some of these things that you would be looking up and using.
Right.
This is kind of the when we have these values in these tables that are nicely pre-made for you to use, these are sort of the experiments they came from.
Well, yeah, that's right. Okay. So in this case, we have, here's our membrane here. We have a C sub A1 is the high concentration on one side of the membrane. C sub A2 is the lower concentration on the other side of the membrane. And so there's going to be diffusion across the membrane from the high to the low. Okay. Let's see. The diffusion of the solute in the x direction is, here's our fixed first law. So that pertains to what's going on here, in this region here. And I'm sorry, I forget how Dr. Babincy defined that. Nevertheless, it's also the diffusivity of the membrane from 1 to 2, from C1 to C2. Okay, divided by L. This is an L, not a 1. So that's the length or the thickness of the membrane.
Okay, so we're dividing out the length here because the diffusivity pertains to how do these materials interact with each other regardless of the scale we're using. And the the term over here and here, J sub SS, like how would you speak that out in full? Like, what would you call that term?
I'm going to have to pass on that.
All right, so it's diffusivity.
You'll have to ask Dr. Bevensey to explain that. Okay, so one thing is this concentration C1 and concentration C2. We don't have that. We do have the concentration CA1 and CA2. So what we're going to do is use the partition coefficient and assume it's the same on both sides. So that if we solve for C1, it's just K times CA1. And so if we put K times CA1 and K times CA2 here, now we have an expression which uses concentrations that we can easily calculate.
And this is checking my understanding here. CA1 would be the concentration of species A, a particular subset of the solution or whatever.
Species A is the one that's diffusing across the membrane.
Okay, so C sub A1 would be concentration of species A, whereas C1 here is the concentration of everything?
Oh, that's a good question. No, actually, C1 is the concentration of species A right at the membrane edge right here. And C2 is the concentration of species A right at the edge here.
Oh, okay, and so CA1 is the concentration of species A, like as it's floating around in this soup.
Right.
Okay, so it's all concentration of species A, it's just specifying where we're measuring it.
Good question. Yeah.
Cool.
Okay. All right. So let's see. Here she's talking about modeling the permeability in without using the thickness. So it's just the partition coefficient times the diffusivity. However, she prefers the one that does use the thickness. Okay, so this is what we'll be using in class. But I guess she just wants you to be aware that someone else may be talking about permeability without the thickness.
Okay. I'm about to run out of battery. So we're skipping the examples because you had PSS and homework.
So we talked about the diffusivity, we talked about its units, we talked about the Wilkie-Chang equation, which is an empirical correlation to estimate the diffusivity in liquids. We talked about membranes and their permeability. And we did not do the examples, but you had that in the problem session. So.
And what I'm gathering from prioritization of which things were, this is a nice to have, as opposed to learn the stuff, is, so one is pretty important. So what is diffusivity? How does it work?
Absolutely.
Be very comfortable with these terms.
Yeah.
The membrane permeability stuff, similarly, and the physical characteristics seems like a nice to have.
I can't speak for Dr. Bevensey.
That's fair. But it seems like that's a, here's more complex things that you might see if you end up having to take into account pore size and tortuosity and all that stuff. Mm-hmm. But in a simple situation, we can just go, that's all been incorporated into some other variable we've looked up.
The partition coefficient and the idea of permeability will be important. It seems to me so. But what makes the permeability what it is in terms of the pore size, that's just something that you should be familiar with.
Okay.
Is my take upon this.
Okay, so it's, what kinds of things affect permeability, being aware of it, not necessarily having to go and do that for every single problem you will ever solve, but knowing that things like pore size matter. All right.
Okay.
I think that's
it.
too.
That's a wrap.